Hello, my name is Gabrielle Rush and this is my Lab 5 report. So in this lab we collected data of a magnet falling through a tube of aluminum foil. We used our Python GlowScript code to model the interaction computationally, and we compared our prediction with our observed data. So the principles used, we used Faraday's law, Lenz's law, Biot-Savart's law, and Newton's second and third law. All of these were very prevalent throughout this lab. So this is my lab setup, and right here I have the magnet, and then I labeled the north-facing side. Here's my aluminum foil, and this is kind of a setup of one of my sets of the experiment. And so the dimensions, the length of the tube was 0.27 meters, width was 0.02 meters, and a radius was 0.015 meters. So here's an Excel spreadsheet of my data collected, and I actually did 10 rounds of data because I have the south side going in first and the north side going in first, and I have the magnet just going without the aluminum foil, just falling from the same height. And so the north average was 2.106 seconds. The south average was 2.33 seconds. Computational model, though, was 2.56 seconds. So actually the south side going in first took longer than the north side, which I thought was interesting. So here's my computational model, a screenshot, and this was kind of the shell code, what I first was getting. This is kind of what the setup was before it fell through. And with the code completed, this is what the magnet looks like when it's all the way through. And so it's red here. And then the time in the tube is 2.562 seconds. The velocity versus time graph here, I have actually a flat line for the velocity, which shows that the forces acting on the magnet falling through were actually consistent. And so here's my code, my GlowScript code, and this is a formula from one of the videos, which was really important on calculating the flux, and I used that kind of throughout here to get all the values that we needed. And so the first question asked was, why can't we use a ferrous tube? And so ferrous metal is magnetic, and it would have ruined the electric field and the magnet falling through because the magnet would have been attracted to it. And a non-ferrous metal is not magnetic, just like the aluminum foil that we were using. So what happens to the magnet as it falls through? The falling magnet induces a current within the tube. We know Lenz's law, the current creates a magnetic field that opposes the field of the falling magnet, which is what induces these resistive forces that causes the magnet to fall slowly. So what happens to the magnet in free space without a tube? So I showed you guys my calculation, and it was really a quick, it was like 0.6 seconds, and so there's no forces to oppose it, so it'll just have gravity. That's the only force acting on it. So computational questions. So which color, red or blue, corresponds to clockwise? And how do we know? So I said red is clockwise, and I know that because due to the right-hand rule, I know that the velocity is downward. And so the right-hand rule shows that my current should be clockwise. And so my computational model, as you guys saw, it was red. So that's why I said red would be clockwise, blue would be counterclockwise. And what happens to the dynamics of the system when you flip the magnet around? So it took longer. It was slower when it was the south side going in first, and faster with the north side going in first. Computational questions continued. The total time in the tube, how does it compare to the real world system, and how do we fix the computational system to be more accurate? So there actually was the cardboard interfering with the electric field, which is why I thought the real world system, that's why it was faster. And so maybe making the computational model more accurate by adding that cardboard dynamic layer. What does the shape of velocity versus time plot tell you about the forces acting on the bar magnet? So it was a flat line showing it's a constant velocity, showing it's a constant force while it's in the tube. So now what if the resistivity of the conductor were reduced? So that would actually reduce the effects of Lenz's law on the falling magnet, and the falling magnet would fall at a regular speed as if the aluminum tube, was not there. So what if there were holes or slots cut into the tube? How would this affect the rings? So it would be, the current would be inconsistent, and there would be an inconsistent magnetic field. And so I said the magnet would fall faster because there would be less resistive forces acting on it. So that's the end of my slideshow, the end of my lab report. So thank you guys so much.